This video will discuss Markov chains and stochastic matrices. Now, a stochastic matrix is a square matrix whose columns are probability vectors, which means their values have to be between 0 and 1 inclusively, and that column has to sum to 1. Now, often we use this when we're talking about transitions in populations, and that can change as to what types of populations we may be dealing with. Now, when we take that stochastic matrix and apply it in a Markov chain, what we're doing is we're looking at a sequence of how the states are changing from one state to the next. And every state is always determined by the previous state being multiplied by the stochastic matrix. So when we want to solve this, we first need to find our stochastic matrix, and we're going to take that stochastic matrix and multiply it by the initial state vector, which we could call x naught, and that'll give us the first state. And then to create the second state, we'd multiply our stochastic matrix by what we just found to be the first state. So it's always taking the stochastic matrix, multiplying it by the previous state. So let's look at an example. Say that we're in a region where there are 15,000 people in rural areas, 35,000 suburban, 70,000 urban areas. And there's a trend of how people are transitioning in these areas, with 85% staying rural, 10% moving to a suburban area from a rural, and 5% moving to an urban area from the rural area. And we can see as the percents go on for each of those different changes. And we want to know what's going to happen to the population over the next 2 years. So the first thing we'd have to create is that stochastic matrix. What's the probability changing of those transitions? So what we would start with are columns and our stochastic matrix, where we have a column for the changes in rural, the changes in suburban, and the changes in urban. And our first row would be, how do we change and move to rural areas? Then how are they moving to suburban areas? And then finally, how are they moving to urban areas? So rural to rural was 85%, or 8500ths. To suburban was 10%, or 1/10. And then to urban was 5%. Now we're going to do that with the suburban. Suburban to rural, 5%, suburban to suburban, 90%, and to urban was 5%. Now we do it with the urban group. Urban to rural was 2%, urban to suburban was 10%, and then urban to urban was 88%. So we have our stochastic matrix, and now we're going to multiply it by the initial state vector, which is our initial populations in those three areas. So it's 15,000, 35,000, and 70,000. Now to find the first year, we multiply those two matrices together. And if we do that, we're going to get 15,900, 40,000, 64,100, which means that we would expect to have 15,900 people in rural areas, 40,000 in the suburban areas, and 64,100 in the urban areas. Now to get year 2, we keep our stochastic matrix and we multiply it by our first state, because that's the previous state now. So x2 is dependent upon x1. We multiply this through, and we get that there's about 16,797 people in rural areas, 44,000 in the suburban areas, and about 59,203 in the urban areas after 2 years. So the question then becomes, what happens if we want to say what's going to happen with this population over a long time? Say no one is added and no one is removed. What would happen to where people would be over a long period of time? And that's trying to converge to a steady state. And they will always eventually converge to this steady state. And what this means is that when I take my stochastic matrix and multiply it by the state vector q, when I multiply them, I continue just to create something that's identical to what that previous state was. That's the steady state vector. So how do we create that steady state to know where are we eventually going to end up? So first thing to recognize is that this is a stochastic matrix times the state vector. And what we could also say here is that this is multiplied by the identity matrix, which is the exact same size as our stochastic matrix. So if we want to rewrite this so that it equals 0, what we could recognize is that we can take the stochastic matrix minus the identity matrix, because we can subtract matrices of the same size, multiply that by the state vector to equal 0, and that's a solvable matrix using the Gauss-Jordan elimination. Now when we do this, you're looking at probabilities minus 1 in the diagonals. A lot of people write those as decimals. Personally, I find it either to change them to fractions or to change everything to whole numbers so that it's easier to do the Gauss-Jordan elimination, especially if you're not using a calculator to help you. Now, as you do this, you're likely going to end up with a free variable. That's what's expected, one free variable. And what you would do is write your state matrix in a parametric vector form. So what this will do is you'll end up with, say, like x3, and everything's going to have some probability based on it. Now, within that vector, you're going to have things as fractions. You want to change those using the least common denominator so that all the numbers in that column are going to become whole numbers. And then you're going to use scalar multiplication to convert them into probabilities. So we're going to go through an example because I know this is a lot written down here. Hopefully this will help seeing the example of this. So what we want to do, we're going to take that exact same problem, but look at what happens if we went out many years with no one being added or subtracted from the population. First thing we create is the steady state vector. So we take our probabilities and subtract 1. Now you see here, those probabilities that I had as decimals, I've changed to fractions. Again, because working with fractions is going to give you a more precise answer than working with the decimals, and it'll be easier in the long run. So if I subtract them, I end up with the negative 3/20ths, the negative 1/10, and the negative 3/25ths on my diagonal, and everything else is positive. So again, you don't have to deal with fractions. I just find it easier than dealing with the decimal values of these. And you can also just change them all to whole numbers, and that'd be perfectly fine too. Now I would do my Gauss-Jordan elimination. And again, you can use a calculator to help you with this. Eventually, you're going to get that this matrix would row reduce to here, where I've got 1 on the diagonals, and then my last row is all zeros, and my third column I've got negative 7/10, negative 17/10. And if I think about, well, what does that mean? Well, that means that x1 minus 7/10 x3 equals 0, and x2 minus 17/10 x3 equals 0. So if I want to think about, well, how would I write my equation? That would mean that x1 is equal to 7/10 x3, x2 is equal to 17/10 x3, and then x3 is my free variable. So if I wrote that in parametric vector form, I would say that q is equal to x3, and then 7/10, 17/10, and then 1. Now why does that matter? Well, the whole point here is I'm going to turn this into a probability vector. So I've got to relate all three of these values here, which are kind of crazy. So I can say, well, what could I multiply x3 by that would at least turn these to whole numbers to start with? The easiest thing, what's their LCM? In this case, it's just 10. So if I multiply all three values by 10, I end up with 7, 17, and 10. And now I'm going to turn this into a probability vector by finding out, well, what is the relationship of each of these values to the total sum of my column. So if I sum up that column, I end up with 34. So I can rewrite this then as 7 out of 34, 17 out of 34, which simplifies to 1/2, and then 10 out of 34, which simplifies to 5/17. And you don't have to simplify the fractions, it's just common practice that you would. Why does this matter? What this means in the long run is that if I think about my population of 120,000 people and they don't change over a long term, 7/34 of the population would end up in rural areas, which is about 24,706 people. Half the population would end up in suburban areas, or 60,000 people, and 5/17 of my population, or about 35,294 people, would end up in urban areas. See, that can be very helpful, and think about a real-world situation when you're trying to determine how do you allocate resources, how do you modify what may need to be done to improve situations, thinking long-term here. Understanding how populations may shift over time can be tremendously helpful in making accurate decisions.